All right, welcome to Module 5, Chapter 8, uh, Traverse Surveys and Computations. The book calls it Transverse. Nobody locally is going to call it that. It's the same meaning, but it's all going to be called Traverse. Your familiarity with the word traverse is probably in the realm of traversing across the countryside, where you go from point to point, place to place in your travels, or maybe on a vacation where you're traversing the up and down the road, meaning you're going stop to stop, stop to stop, and that's what surveying does in a traverse um, survey. A traverse survey is another name for control survey. It will establish primarily horizontal control. The importance of horizontal control is that it's the basis of any survey. So first thing you're going to do is go out and look for property corners, and you're going to establish some sort of control loop around the construction site, uh, so that there's survey control all around it based upon something you know. And that control is going to be put in places where it's difficult to disturb, we hope, easy to get to. You don't want to have to, you know, get through, make it very difficult to get to it because of the need to reuse the control over and over, sometimes even on a daily basis for construction stakeout. So the traverse is very important, and the book goes into a lot of in-depth calculations and takes a long, hard look at how you go about doing things with a traverse. And we're going to go through it so that you can understand it and see what happens. But I can tell you computers do this now. And not only computers, the types of closures that the book discusses for surveyors in the state of Maryland, we don't even use that anymore. It's only for a reference. And as we get further along, I'll explain what is required in the state of Maryland. But let me go ahead. I'm going to share my screen, and we're going to get through the slides. And again, I warn you that this will be a long video. So get to a point, pause, take a break, come back. Um, I'll probably be doing the same thing. There's a lot of material to cover and a lot of slides. So here we go. We're going to start sharing. Let's make this a slideshow. First of all, let's hang in there a second. Let me share first. All right, I want to make this a slideshow. And then this will be a little easier to follow. All right, so here we are, chapter 8, and we'll get moving along here. So it's called the traverse. It says here it's a form of control survey. That's what we talked about. It is used almost on every single property where there's an engineering project or boundary survey that's required. It's used almost on every single one, and it's also used to set up control for construction sites. The book talks about two different types of traverses, one open and one closed. I can tell you surveyors don't think that way. The open traverse refers to, in the book, is something surveyors would not do. It's starting from a known direction, and we're going to see here in a little bit, and then just going off, like you're going down the road surveying, and you never check into anything. You don't know where you ended up at or anything along those lines. A closed traverse here discussed will be a loop of some sort. The book discusses that, and when we get to closed traverses, I will explain another form of closed traverse that surveyors refer to as an open traverse, but it's not really open. So this type of traversing, this type of control work, You would start here at 0, 0. You would turn in, you have a known direction. You're sitting here between this point number 631 and 632. And you turn it an angle and you go a distance and you keep going and you get to some point, but there's too much error in this, and surveyors should never do this, and most of them would never do this. There's too much error just to move down here and not know where you are. So that's why we don't want to use what the book describes as an open traverse. What we're going to look at here is more of this is a closed traverse loop. The next several slides are going to pertain to this particular loop here. We have an angle and a distance between every one of these points. So in theory, we would know a direction we started, which would be right here. And we would turn all these angles and distances. And when we get back to here, this angle should turn back onto the known direction. The problem is we have error in everything we do, and we hardly ever hit that known direction. And because of that, we have to adjust the traverse and compensate for the errors we've made. So here is a set of notes. I wouldn't be too worried about that. This is one thing I want to do. I do want to point out though. Let me zoom in a little bit here if I can. So right up here, it talks about direct, double, and mean. So what you should be doing, surveyors, is turning multiple angles at the same location. We talked about that as a way of eliminating errors in the prior chapters. So in this case, when you do a traverse, you should turn multiple angles. The state of Maryland requires you to measure every angle 4 times. I measure my angles most of the time 8. 8 times I measure an angle before moving on, and it has to be, those 8 can only differ by so much, a small amount, or I do it all over again. So you don't need to worry about open-end traverses very much at all. Here is a closed traverse loop. You would never take field notes like this. One of the reasons is the distances aren't there, and the way people take field notes is totally different from what this book is showing you. However, it's not that important. I'm not going to test you on it, and you have a data collector now. Even construction managers and people on construction crews will often have a data collector that will store all the angles and distances as they're turned. So you notice this one here, this is notes and tape. I mean, people are pulling, you're not going to pull a tape and a chain to do a traverse anymore. It's just not going to be the case. What this is showing you here is a situation up here on this shape. This particular shape here is a closed loop. Here's your angles, but what we have happening is we're supposed to end up with 540 degrees. If you remember, there is a little carryover from the first part of the semester. We have 5 angles, so to determine the number of degrees, the total number of degrees in the polygon is going to be 5 minus 2, which is 3. 3 times 180 would give us 540 degrees. The problem here is that when we turn these angles at A, B, C, D, and E, we actually total up to 540 degrees and 1 minute. And so we've made a mistake. And how do we do that? We adjust the angle. We adjust each angle equally, and it will balance these angles out equally because we turned 5. And you end up subtracting a fifth of a degree, which is 12 seconds, from each one of these angles, and you will adjust them over here, and you have 540 degrees. Now, that is something that is still done, just so you have an understanding of what you've got going on and what kind of a raw product you've turned in. So the next thing we want to look at is, and the book begins to explain the differences between azimuths and bearings. Um, the book's going to cover bearings first, then azimuths. They each have their purpose. Azimuths are easy to deal with in math, and a bearing is what you normally see on a compass bearing. And then normally a bearing is what you'll see on all your plats and in your deeds are all bearings. So bearings are referenced from north or south, and they reference east and west. And we're about to see what bearings look like. A bearing, in this particular case here, from K to 1, is north 21 degrees 40 minutes east. And that's exactly what it tells us right here, the line from K to 1. K to 2, I said it references either north or south for bearings. K2 is south. And then you turn this way, and you actually would be turning 71 degrees in 30 minutes to come up with this bearing. So there's 90 degrees between each quadrant, 360 in the circle. And this is how you determine bearings. There's 4 quadrants: northeast, southeast, southwest, and northwest. They also coincide with what it looks like on a compass. So bearings are what we use most of the time. I very rarely ever use an azimuth. It just isn't something we need to do anymore. So also the thing with bearings is they're like reversible. So a bearing, if you remember a line from geometry, it's never ending, right? Goes all the way through. So if this is your, right here, is this your compass? This same line from K to 1 is also from like K, an extension of like 1 to K. It comes down here. So whatever is northeast is also southwest. And in here, we go up north, 2140 east is the same. If we move this up to here, it's the same as going south, 2140 west. That's very important to know, and it's going to be very useful in dealing with a traverse. So here's how we compute bearings on a traverse. You have a position here that's given to you. It's where we start from. This would be the initial setup, and this would be your initial backsite. There is a video that I downloaded or linked off YouTube where a guy runs a small traverse, and I think it's 5 stations, and he explains exactly what he's doing, and I suggest that you watch that video. You'll gain a lot from it. So here, when we're looking at this bearing, we're looking back in a southeast direction. We turn this 101 degrees 28 minutes, and we will get a new bearing on this line. And that particular bearing is given to us down here at north 71 degrees 11 minutes east, and you come over here. And you continue then, so then instead of northeast, now you say that same bearing is reversed. It's going southwest now as I sit at this point, and I measured this angle. So that's why it's important to know that the bearings are reversed, because see here, we were given this north 7111 east right there. Now we reverse it, and we turn this angle again. So that's how bearings work, and that's how they work for a traverse. I'm not going to go over every single aspect of this slideshow because there's plenty of it to go through it. Okay, so here, what we have is a circular graph, and this just simply shows you how azimuths are calculated. 0 is the same as 360, 90, 180, and 270, 90 degrees for each quadrant. We're no longer dealing with north and south. So anything in this quadrant is just 10 degrees. We got 10 degrees, 20 minutes, because we start here and we went over 10 degrees. But here we start over this way at 90, and then we add to it 18 degrees and 46 minutes. And the same thing down here, 180 plus 3807 gives us an angle from K to 3 of 218 degrees 07 minutes as an azimuth. Always measured from due north, straight north. You turn all the way around, so if you stop just short by 1 degree, your azimuth would be 359 degrees. So you don't worry about directions now, and it has its place. You don't have to worry about north and south or east and west, but it does have its place in the survey world, and they're going to show you that coming up. It's just you don't have to do it this way anymore because of computers. So any azimuth to the right of the meridian, 0 to 180, is the same azimuth if you were to add 180 degrees and you end up on the left side of 0 to 180. So in this particular example, we have K to 1 is 10 degrees, 20 minutes. Its azimuth is going to be 10 degrees, 20 minutes. However, from 1 to K, we would also know that it's 180 plus 10 degrees and 20 minutes, or right there, 190 degrees and 20 minutes. So that's how reverse azimuths work. Here's a survey. It's the same thing that was done with the angles and the distances. And it was done in azimuth, so it's not that much different, not too big a deal. Here's something that you want to, so here's what it talks about with azimuths. We have clockwise directions to compute them. Each one is computed by subtracting an interior angle from the back azimuth, just like we said, a reverse, and then you measure your angle. Counterclockwise direction of the computation. Each azimuth is computed by adding the interior angle to the back azimuth of the previous course. So always reversing your direction and adding to the angles. This right here is called a polar tie. And what the significance of the polar tie is that it explains a bearing and a distance, a bearing and a distance right here. And this is called a polar tie. We start at some origin. We go northeast, 71 degrees and 11 minutes for a distance. We end up at B. But the next thing we're going to look at is another way to get here utilizing coordinates. These are latitudes. If you look at your globe, you have latitudes and longitudes, right? Latitudes go from the North Pole to the South Pole, and longitude are the longer lines that, excuse me, the longer lines that move east and west from Greenwich, England. So they originate, so the latitude lines originate around the equator and continue getting smaller and smaller circles as they approach the North and South Pole. That's the latitudes. The departures are how far off they are from that meridian, and those will be measured with the longitudinal lines that go from the North Pole down to the South Pole. All right, so that's a rectangular tie. Here's how we begin to talk this discussion of computing latitudes and departures. And I tell you what, I am going to do my best here to pause this and pause the recording. And I'm just going to take a little break and get back to this. So hang on. All right, I am back. And let me go ahead and try to share my screen again and continue here with this slideshow. What we have now is the computation of latitudes and departures. And you're going to see where this comes into play and becomes very important as we look at distances and correcting the distances measured in the traverse. And you're going to see this will be applicable to things you might do in the future about computing coordinates on a point so that you can put it in a data collector and have your total station or your GPS receiver take you right to the point. Your latitude, again, is the difference from north to south. It's also called a northing, as we're going to see here in a little bit, and that's why this n is in place. So the delta n is determined by taking the distance measured and multiplying it by the cosine of the bearing that you're on. The departures is done by taking, which is your easting, and it's done by taking the distance and multiplying it by the sine of the azimuth to come up with a different answer. And that's how far it is from east to west from the main meridian. So here, what you're looking at when we look at latitudes and departures, that's north and east, keep that in mind. The first thing from A to get over to here, it's rectangular. How far up we got north, how far over we went east. This is your latitude, that's your departure. And you would be able to go through this and use the angles and distances that we've already computed, the corrected angles, and you would get these differences in latitudes and departures. Now again, I'm not going to ask you much on this. I'm running through it so you have an idea how you would go about correcting a traverse. But you're just not going to have to do it. You're not going to have to do it by hand either. If you end up in a construction situation where you're surveying for a construction company, your computer is going to do all this for you. So here's a little chart. It tells you the distances and the bearings that were taken from the previous, everything was figured out previously. And it gives you the changes in latitude and departure. And one of the things that you'll recognize was that when you get to the end, all of these added up should equal 0. And the same thing over here. All of these added up should equal 0, but they don't. They don't equal 0 at all. So what we need to find out is we want to solve for the linear error of closure. And we do that by taking the square root of the sum of all the latitudes, which is actually 0.13, adding it to the sum, I'm sorry, not square root, the square of the sum of the latitudes plus the square of the sum of the departures. We're figuring out the hypotenuse of a right triangle, and we're using Pythagorean theorem to come up with this right here. Our traverse has an angular, has a linear error of closure of 0.17 feet. And we would then, there's a way to take the information and adjust it so that everything ends up being zeroed out. See if it gets us here. The compass rule is, again, it's something that most surveyors would be familiar with and would make reference to. It takes and distributes the errors in the latitudes and departures, and it does it based upon the length of the line, not anything to do with the angles, but the length of the line that was measured is, and the latitudes and departures are distributed proportionately to that line that's measured. one of the things that brings up, and we just discussed it, is this issue of rectangular coordinates. Um, Utilizing rectangular coordinates, we're able to do a lot of things and bounce around and adjust things by a coordinate, and then ultimately use the coordinate and stake out. And that's what we're after here for construction. The coordinates are basically the X and Y axis of a graph, with the X being the east to west, and the Y being north and south. Um, Here, what we're looking at is, it talks about a transverse Mercator grid, Lambert grid. Chapter 9 is going to talk a little bit about this, but you don't have to worry much either. Again, if you really are into surveying and you have to really work for in a construction situation, your data collector and your computer are going to handle this right here. All right, so what we've got is an assumed datum. A lot of times surveyors would do this. They would assume 1,000 or 10,000 right here for north and east. And then they would figure everything out. And from the information that we saw before, you would apply the latitude right here, the change in latitude, and then this is your departure. And you would get that change based upon this bearing and distance. Once you have those numbers, you would add them or subtract them if you have a negative sign. Like if you come this way, you're going down, it's negative, or subtract them from this coordinate to get a new one. And you do that all the way around until back to the beginning. And if you have adjusted your distances, if you adjusted your distances like right here, went too far. I'm trying to find it for you right here. So you would adjust everything so that you would adjust out this distance. You would change all your latitudes and departures proportionally based on the distance shot. And then you would rerun these numbers and you would end up having 0, 0. And that is a compass rule adjustment. One of the things that I needed to point out is that surveyors don't use compass rule anymore. The compass rule has been replaced by least squares. The least squares method of balancing your traverse information is much more indicative. It doesn't assume all areas are equal, and it does a much better job for you in handling the closure. And it's something that, as far as math goes, it's the one thing in surveying I cannot do. The math entailed in this is a huge amount of math. It's a statistical analysis of all of your information that you measured. It's all analyzed as statistics and balanced out, and it's something that is above me and beyond me. So again, we were looking at the rectangular coordinates. I told you we were looking at something different here in chapter 9. These are the different coordinates that we end up getting. And the next thing we want to do is station coordinates using balanced latitudes and departures. So this was everything fixed correctly. The next thing that the book wants to try to show you is the area by rectangular coordinates. And you can kind of look at this sketch, and it's gonna basically start defining triangles and squares everywhere to be able to identify what the area is in this shaded portion. Now, you can always come up with areas using triangles and rectangles. However, surveyors use two other methods. One, their data collector computer will tell you. Two is called a double meridian distance, a manner of coming up with the area of something utilizing the coordinates. Again, you're not going to have to do that. All you're going to have to worry about is what goes in a computer to calculate your area for you. But you're certainly welcome to try to figure out triangles and try to get it done that way also. This was just a picture of how they went about using triangles to help get the area. So that brings us to a conclusion of the slideshow. And I will stop my share and get back to looking at you here for a minute. This was a lot of information. It was a bunch of stuff that you're not going to have to do, but the things that I pointed out as an emphasis and discussed a little bit are the things that are a little bit more important and the things I can test you on. And that's more like theory versus putting it all into practice. So I'm going to take a little break and I will be back with the Chapter 9 lecture on satellite receivers.